All right, here we go at balancing chemical reactions overview. So we have chemical change. Typically, you'll see if something fizzes, there's a smell change or aroma change, a color change, a temperature change, or a new substance. This list is not perfect. Okay, when you have soda and you shake it and you open it and it fizzes, that is not a chemical change. That is the carbon dioxide coming out of solution. Temperature change on the stove. If you heat something up, the temperature is changing, and that'll be a physical change if it's something like the water is converting into water vapor or steam. But in general, that is your first sign to look if it's a chemical change. If it's a chemical change, we use a chemical reaction where the reactants are on the left side. Those are your ingredients you're putting together, and the products are on the right side. That's what you're producing, creating, synthesizing. Okay. When we make these new substances, we are not magically creating new elements or new atoms. We're taking the same atoms from the ingredients and we're just rearranging them in new forms to make those new substances. Since they're now in a different arrangement, then they have different properties. So sometimes on the chemical reaction, you're going to see a S in parentheses. That just means it's a solid state. An L, a liquid state, a G, a gaseous state, and the one new one you might not have heard of is AQ for aqueous, dissolved in water. Okay, so if you have a substance that's dissolved in water, like an acid, acids are always aqueous, then you would see that little tag behind it. Okay, if you see a solid on the right side, that's a precipitate. That's the product raining down into solid form at the bottom. A lot of people always like to think, is water wet? Well, water is not aqueous. Water is a liquid and it's a pure substance. So there's a whole big debate we could do on that. All right, so when forming water, 10 grams of hydrogen gas and 79 grams of oxygen gas was used. There are no leftover reactants. Hydrogen gas and oxygen gas were used. If they were used, that means they are reactants. So on the left side, we have 10 grams of hydrogen gas and 79 grams of oxygen gas. Nothing else was used. We have no leftovers. So that was used in its entirety. So the mass of the water, and remember, you could always pause to fill in the blank to make sure that you are ready for that test. The mass of the water is going to be 89 grams of water. Why? Conservation of mass. Mass cannot be created nor destroyed. So the same number of each element on the left is on the right. The same total mass on the left is on the right. Conservation of mass. Mass cannot be created nor destroyed. Now, sometimes you'll get a higher level question, so always make sure you're reading it carefully for what is going on. So here we have iron 4 sulfide reacts with. So right now I see that reacts with, and I'm going to put a plus because they're being put together. Iron 4 sulfide is being put with magnesium chloride. It's being put there. That means those are ingredients. So iron 4 sulfide is a reactant. Magnesium chloride is the reactant. To form, to produce, to yield, to create, to synthesize. You could see any of those things, but that means we're going to need our yield arrow right there. We're forming the products of iron 4 chloride and magnesium sulfide. So in this reaction, we have 2 reactants and 2 products. What is the ratio of the product coefficients? Lots of details there. We got to create a balanced chemical reaction first. Iron 4 sulfide. I see a Roman numeral. What does a Roman numeral mean? It means the charge. So this is going to be an ionic bond. Iron is capital F lowercase e. Iron 4 is in a compound with sulfur, 2-. Where do I get those charges? From the groups on the periodic table. It's a cation, +4, An anion, -2. Opposites are attracting, so we have a crisscross ionic bond. The 4 from the iron goes with the sulfur. The 2 from the sulfur goes with the iron. So our first reactant, Fe2S4. I can simplify those. Ionics should always be simplified. The lowest mole ratio, or the lowest atom ratio for you guys. Fe1S2. Oh, which I can go even further. FeS2. So iron 4 sulfide looks much different than maybe you pictured in your brain, but that is FeS2. Be aware of your capitalization. New element, new capital letter, just like new sentence, new capital letter. FeS2 reacts with, so I get a plus, magnesium chloride. Magnesium's a +2. Chlorine, remember that ide is just telling me that we're in a compound, is a 1-. Magnesium, 2+, chlorine, 1-. I am going to crisscross again. The 2 goes down with the chlorine. The 1 goes with the magnesium. When I rewrite, I'm just going to write magnesium with 2 chlorines. 1 magnesium balances 2 chlorines. And that is going to form, so I need my yield zero, iron 4 chloride. Iron with a +4 charge, chlorine with a -1, crisscross. And again, I'm not going to rewrite the 1, so FeCl4 is my iron 4 chloride, and magnesium sulfide, magnesium 2+, sulfide 2-. This is a basic ship. This relationship is perfect as is. I don't need to crisscross, but if you do, just make sure you simplify afterwards, because ionics are always in their simplest form. So I have iron 4 sulfide reacting with magnesium chloride to form iron 4 chloride and magnesium sulfide. That is the equation. So we now have the sentence figured out. So at this point, you cannot change the words. FeS2 has to stay FeS2. Same with the other compounds. We have to change what? Our coefficients, so that we have a balanced chemical reaction. I have 1 iron on the left, 1 iron on the right. So for right now, I'm going to leave it as is. I have 2 sulfurs on the left. So now I need 2 sulfurs on the right. Remember, this guy works like parentheses in math. So 2 times 1 gives me 2 magnesiums. 2 times 1 sulfur gives me 2 sulfurs. How did I know that they're 1s? Because remember, we take those 1s off because we're lazy and we don't have to hit the subscript button and then write the 1 when it's a 1. So if you don't see anything there, you're multiplying times 1. All right, magnesium, 1 magnesium on the left, 2 magnesiums on the right. Why? 2 times 1 is 2. So I now need 2 magnesiums on the left. Remember, you always go to the side with the least. So I have 2 magnesiums on the product side, and I have 1 magnesium on the reactant side. The side with the least is magnesium 1 reactant side. I need to make it a 2. I don't change the subscripts because that would be making my spelling wrong. Spelling of my compound. I can only change the coefficient. Something times 1 is 2. 2 times 1 is 2. Chlorines. 2 times 2 is 4 chlorines. And there's nothing here right now, so we're just going to assume it's a 1 for right now. 1 times 4 is 4 chlorines. So I'm going to go back and fill in 1s on all those empty spots, and just double check again that I did not make any silly errors when I am doing these calculations, because sometimes I do. 1 times 1 is 1 iron. 1 times 1 is 1 iron. 1 times 2 is 2 sulfurs. 2 times 1 is 2 sulfurs. 2 times 1 is 1 magnesium. 2 times 1 is 1 magnesium. 2 times 2 is 4 chlorines. 1 times 4 is 4 chlorines. I am balanced. Conservation of mass has been met. I have 1 mole of iron 4 sulfide reacts with 2 moles of magnesium chloride to form 1 mole of iron 4 chloride and 2 moles of magnesium sulfide. And then after all that, I got to go back to the question, what is the ratio of the product coefficients? 1 to 2. These large numbers in front are your coefficients. Leave it in whatever order they tell you. Okay? So in this case, my ratio of my reactant coefficients is equal to my ratio of product coefficients. That does not always happen. There is no conservation of moles. So read carefully on what they are looking for. C2H6 reacts with oxygen gas, O2, Brinkelhoff, because it has 2. He always wants his twin. He's a diatomic compound, and forms carbon dioxide, CO2, that's a covalent bond. That's why we could use the prefixes there. And water. Water's formula is dihydrogen monoxide. C2H6 reacts with oxygen gas to form carbon dioxide, which I also know is a gas, so I'm just going to add the state symbol there, and water, and I'm going to assume water is a liquid. It's not always. Okay. C2H6 is also a gas. You do not need to know that, but as long as you have less than 8 for your carbons, you're less than an octane, you can assume that it is a gas status. Look at this standard form. CXHY plus O2 yields CO2 plus H2O. This has to be a hydrocarbon combustion because I have a hydrocarbon. My X is 2, my Y is 6, plus oxygen, yielding or producing carbon dioxide and water. So it's matching my standard equation for combustion. Combustion has a specific set of rules. Balance the carbons, then balance the hydrogens, and then balance the oxygens. And then you still want to go back and double check you didn't have any errors. 2 carbons, so I'm fixing just the coefficients at this point, not the words. 2 times 1 is 2 carbons. Hydrogens, 6 hydrogens. Something times 2 is 6. 3 times 2 is 6. Oxygens, 2 oxygens here, and just be careful on this side. I have 2 times 2, or 4 oxygens and carbon dioxide, and 3 times 1. Remember, you don't see it there, it's a 1. 3 times 1, 3 oxygens here. So on my right side, on my product side, I have 7 product oxygens. On my left side, right now, I only have 2 reactant oxygens. Because of conservation of mass, I know they have to equal. So I go to the side with the least. That's the 2, and I got to fix his coefficient. Something times 2 equals 7. 2x equals 7. X equals 3.5. You can also leave it in fraction form. Frankly, I leave it in fraction form when I do it myself. And this guy over here just gets a 1. All right, let's double check. 1 times 2 is 2 carbons. 2 times 1, 2 carbons. 1 times 6, 6 hydrogens. 3 times 2, 6 hydrogens. 3.5 times 2, 7 oxygens. 2 times 2 is 4. 3 times 1 is 3, 7 oxygens. Now, this is considered bad grammar. Okay, bad grammar if we're going to continue using that a chemical reaction is the sentence. And why is it considered bad grammar? Because I have a fraction in my coefficient spot. So if you have a 2 or a half, sorry, if you have a half in your coefficient spot, like we have here, if you have a half, then you need to multiply all coefficients by 2, all of them. Yep, every single one. So 1 times 2 is 2. 3.5 times 2 is 7. 2 times 2 is 4. 3 times 2 is 6. So your actual answer is 2 moles of C2H6 plus 7 moles of oxygen gas give me 4 moles of carbon dioxide and 6 moles of water. You'll want to make sure you're always showing your work unless it's an SOL, and most of the time on the SOL, they are just going to be giving you multiple choice. One of the things they like to get you on is sometimes the multiple choice answer is, what is the sum of the coefficients? So that is why this problem is not done just by balancing. You have to sum the coefficients. So if you had this in improper form, you would not get any points. My coefficients, 2 plus 7 plus 4 plus 6. So my sum of my coefficients is 19, and that is what you would select on the answer. They could just also ask, how many moles is carbon dioxide? Moles is just another name for your coefficients. 4 moles of carbon dioxide in this balanced reaction. You would get 0 points for 2 carbon dioxides. All right, so I have 2 moles of sodium hydrogen carbonate. Okay, so 2 moles of sodium hydrogen carbonate decompose into 1 mole of sodium carbonate. Oh, carbonate's a -2 charge, sodium's a +2, so I got a crisscross there. And 1 mole of carbon dioxide. And what other product? So even if I didn't know about the crisscrossing here, notice I didn't crisscross on this first one because sodium and hydrogen give me 2 positives and carbonate automatically has 2 negatives. So those guys worked out, but they did not give you any sodiums over here. So that's going to help you solve the problem, even if you did not get that crisscrossing quite right. What is left over? I have 2 sodiums on the left. I have 2 hydrogens, 2 carbons, and 6 oxygens. What did I do? I just multiplied times 1. There's 1 sodium, 2 times 1, 1 hydrogen, 2 times 1, 1 carbon, 2 times 1, 3 oxygens, 2 times 6. So remember that coefficient in front acts like a parentheses in a math problem. What do I have on the other side? 2 sodiums, 1 carbon, 3 oxygens, and in carbon dioxide, carbon C, 1 carbon, 2 oxygens. Okay, I'm putting them on the same line because I got to ultimately add them up. On my reactant side, I have 2 sodiums. On my product side, I have 2 sodiums. They are balanced. On my reactant side, I'm going to skip down the carbons. I have 2 carbons. On my product side, I have 1 + 1, 2 carbons. They are balanced. On my left side, 4 oxygens. I have 6 oxygens. On my right side, I have 3 + 2. So I only have 5 oxygens on my right side. I'm going to put parentheses so it doesn't look like 50. How many do I need? I go to the side with the least. I need to add 1 more oxygen. So I need an oxygen over here. Now let's go back to my hydrogen. 2 hydrogens on the left. There is no hydrogens on the right. So I'm going to add 2 hydrogens. Now, if I add 2 hydrogens like this, that's not going to work because that means I'm adding 2 hydrogens and 2 oxygens. What did I need to add? 2 hydrogens and 1 oxygen. So my answer is 1 mole of water. So you play that missing game if you get one of those. And that's all for today.